In this video, we'll initially have a short segment on partitioning and then talk about linearizable databases in depth. This video goes hand in hand with the previous video on replication and builds upon some of the concepts introduced in the previous video. So what is partitioning? Partitioning is you have a large amount of data, let's say names from A to Z, and because all these names can't fit in one database node, the size is too big, you will distribute the ranges of your data across different nodes. So from the picture, one node will contain names from A to H and the other node will contain names from I to Z. So there's different schemes by which you can choose what name will belong to what node, or to put it in better terms, there are different schemes to determine how to distribute the data and allocate it a particular shard. So one is range-based partitioning. You can arbitrarily create ranges, like in this case, A to H and I to Z, and then assign a specific shard with its followers to that particular range. So what are the pros for this? Pros for this is it's pretty easy to implement and it's great for range queries. So if you have a SQL statement to select names from A to D, you know that it just has to touch this particular node 1. The cons for this is you are likely to have hot shards and it's very likely that you'll have unequal distribution of data. So in this case, let's say it's very uncommon for names to belong in the later sections of the alphabet. So in this case, shard 2 is very likely to be touched infrequently as compared to node 1. So the load balancing over here is not maintained. Another approach to distribute data is with the help of a hash key based partitioning. So you take in your input key, you will apply a hash function and take the modulo with respect to the number of nodes or partitions that you have. In this case, you have 3 nodes and the initial input is directed to node 2 and the next one to node 1. So the pros for this is, assuming that you have a pretty good hash function, you are going to have a pretty equal distribution of data across the nodes for the most part. The cons for this is it's inefficient for range queries. So because your hash function's main goal is to distribute data equally, hash functions over here, if you have range queries over here, it'll be directed to multiple nodes. Let's talk about some optimizations for range-based querying when we deal with partitions. Now, it's more often than not that our range-based querying won't be on the basis of just one field. In some instances, it can be on the basis of some other field. But when you arrange your data into that particular node, you'll arrange it on the basis of some key. So in this case, you are sharding the data based on the name. So this is the data of some basketball players with their heights over here. So initially, let's say node N1 and N2 exist in the picture, and you will direct your data A, B, C to N1 because the range that N1 accommodates will be A to C and N2 will be D, E, F. Now, if you have a SQL query like get details for all players in the names ranging from A to C, it's pretty easy to execute that query. Just direct that query to node N1 and fetch all the records that exist in this node. But what if you have a query, a range-based query that exists on some other field, for instance, on the basis of height? So what if you have count of all players where the height is more than 6 feet? So ideally, over here in this case, you'll have to go to each individual node and read the records that exist over there. And even then, these records won't be sorted because the primary attribute on which you're sorting it is on the basis of the name. So the primary index over here is the name rather than the height. So one fix that you can do is in each node N1 and N2, let the primary index be the name, but let's also have a secondary index, which is on the basis of the height. So if this is N1, N2, this is the primary index, which is sorted on the basis of the name. Let's also have a duplicate copy, which exists in N1 and N2, but you're sorting it also on the basis of the height, which is the secondary index. So you're maintaining an additional index on the basis of the height. So again, if you get a query now, which says fetch the count of all players whose height is more than 6 feet, again, you're going to go to each node, but the access time on each node is going to be log n rather than linear time. But we could try and optimize this even further because we are forced to touch each and every node over here, and that possibly won't scale well. So the first approach that we've seen here is local secondary indexing. where you need to read from multiple nodes. So you're in local secondary indexing, you're maintaining a secondary index on height in each local node. So node N1 initially contains data ABC, and that is your primary key, your primary index. You're also maintaining a secondary index on the data ABC on that same local node. So local secondary index, you need to read from multiple nodes, and any write that comes in, if you want to write a new player, you just have to touch one node. So let's say you have to write a new player, which is G. So direct that to N2 and add G over here and the height. The contrast to this is global secondary indexing. So let's have the same use case. One query could be fetch the details of players whose names are from A to C. In that case, no worries. We already have the primary index on the base of the name. So you can just direct your query to node N1. But what if you have a query like count of all players whose height is more than 6 feet? So in this case, you will have to direct your query to all the nodes. So in the case of local secondary indexing, you had this data ABC on node N1, which is sorted on the base of the name, and you're also creating a local second index on the base of ABC and sorting it on the base of height. Global second indexing requires you to sort a global range of data and distribute that across the different nodes. So when you get a query like count of all players whose height is more than 6 feet, I don't have to read each individual node. I just have to be directed to a certain node containing that range. So what does that mean? In global secondary indexing, I'll have my global data over here, which in this case is A, B, C, D, E, F. I will sort that on the basis of whatever secondary index parameter I have, which in this case is the height, and then direct it to the different nodes based on the height ranges. So what is the consequence of this? So N1, the primary index, was on the base of the name, and you originally distributed data on the base of the name, which in this case is A, B, C, and D, E, F over here. But because you're also distributing global data across the nodes, node N1 can also contain data which is not local to it. So in this case, N1 contains B, E, D, but we know that E and D are not local to it originally. So now if you get a query like get all names from A to C, well, no problem, just direct it to N1. It's already the primary index over here. But if you get a query like count of all players whose height is more than 6 feet, I know based on the distribution of my global secondary index on the base of the height, I know what range my 6 feet plus data will lie in N2, and I will direct my query over here. So what is the downside of this? The downside of this is the nodes will have to contain data which is extra to it, which is not local to it. So global secondary indexing, the local nodes, in addition to their local data, will store extra data based on the global secondary index that is created. A pro for this is obviously very efficient when it comes to processing range queries or range queries on multiple parameters. If you have a range query on a third attribute, you can create again a global secondary index on that attribute as well. The cons are, if you have to create a new player, let's say the player is going to be G, whose height is 5 feet 6 inches. So you know that G will have to be directed to this particular node because let's say this node, the primary index is on the base of the name and the range is D to G. But don't forget, we also have a global secondary index to maintain. So let's say the N1 will have data from 5 to 510. So in this case, based on the global secondary indexing partitioning, I will move this player also to N1. So N1 will also store the copy of G because we are maintaining the global secondary indexing over here. And obviously G will be sorted. So G will come here on top. So that is a con, right? You need to write to multiple nodes when you create a new player. So you'll have to deal with distributed transactions. So when it comes to distributed transactions, you will have to implement it using either two-phase commit. But we saw that in the previous videos, two-phase commit is very resource heavy. It has its own constraints. So an optimization could be to use the Saga pattern. Saga pattern can be implemented using either the central coordinator approach or using choreography between the different nodes. This has been covered in video 1. This is the timestamp over here. So distributed transactions comes up a lot when we deal with partitioning and directing data to different nodes. So far we've seen range-based partitioning, where you create these arbitrary ranges of data and distribute data belonging to a certain range to an assigned partition. And we've seen optimizations for it if we have queries on other attributes using local secondary indexing or global secondary indexing. We've also seen a major drawback with the range-based partitioning approach, which is it is prone to having hot shards. You can have ranges which won't have a lot of data in them, and that particular node won't be accessed as much. And you can have certain data, certain ranges, which are more prone to get accessed, and you'll have a lot of bottleneck on that particular node. We've also touched briefly on another scheme of partitioning data, which is on the basis of the hash ranged based partitioning. So in hash range based partitioning, you have your input, get a good hash function, and mod it on the basis of n, which is the number of shards that you have. So the problem with this is, what if n changes, and n is realistically bound to change in a distributed setup. So in this case, we need to relocate all the entries that are there across our system. So let's say node n1 has 100 entries, n2 has 500, and n3 has 1000. And you have a new node that comes in, or let's say you have a node that fails. So in this case, obviously the output of a hash function mod, the new value of n, will change, and all the entries will have to be relocated. So we need a smarter way to distribute our keys such that if the value of n changes, the number of keys that have to be moved around is very minimal. So in comes a technique called consistent hashing. So consistent hashing is a smart way to distribute keys across your different partitions. And this technique is also practically used to implement load balancing across nodes. So this is consistent hashing. Assume you have A, B, C, which are your original three partitions, and you'll try and create this logical ring. So you'll have A over here. Let's distribute B randomly somewhere else in this ring, and C over here randomly somewhere else. Let's also decide on some value K, which in this case is 2. And if K is 2, it means the number of duplications of our shards on this ring will be K, 2. So because K is 2 over here, A is over here, and you'll also have A dash over here, which is its duplicate. Similarly, B is over here and B prime is over here, C with C prime. So again, this ring is logical. There's no such physical ring that exists. This is a logical ring that you're creating. You're assigning A to some random position on the ring, B to some random position along with its duplicates, A prime, B prime, C prime. So you'll pick a K. If K is 2, each shard gets replicated K times over the logical ring. And the logical ring can be thought of as a clock with, let's say, the range from 0 to 100. So in this case, let's say this section is from 0 to 15. This section is from 16 to 31. This section from 32 to 47, so on and so forth, all the way to 100. Now, if I get some input, so let's say the hash of some input, I will obviously mod it with respect to 100. And let's say it gives me 49. So it is directed over here. But when I assign the node, let me move clockwise. So I'll assign it to node C prime, which in this case is just C. So depending on the hash, move clockwise to find the first node on the ring and push data to that node. So if I get a hashed output value of 15, it comes in this section, and I'll just move clockwise and see that, okay, it belongs to node B. Now here comes the interesting part about consistent hashing. Let's say I decide to remove node C for whatever reason. Let's say it fails. Then in this case, I don't need to redistribute the keys to all the nodes. So whatever keys are in C, I'll just redistribute them to whatever nodes are adjacent to it, which in this case is A prime, B prime, or rather A and B. Similarly, if I were to insert a new node, let's say D in between here, I don't need to rebalance the keys across nodes. I just need to fetch some keys from A and put it to D, fetch some keys from B prime, put it to D. So let's say with the introduction of D, a new range is 90 over here. So you'll have this from 80 to 90, and this section over here from 90 to 100. So when I have D over here, I'll go to node B and I'll check all the keys whose hashed range, the output is from 81 to 90. So all those keys which are from 81 to 90, I'll just direct them to node D. Now, if we remove a node, we're not rebalancing data on all nodes, just rebalancing a very small range. So assume n is the total keys that we have and m is the total number of shards that we have originally, a, b, c. And let's say k is the duplicacy factor. So in this case, the total nodes, the total dots that you see on the logical ring will be k into m. So let's say this is a over here, this is a prime over here, and this is a double prime over here. So in this case, k is 3. So each node will have obviously n keys divided by the total dots that you see on the ring, which is n by k into n keys. So on rebalancing, the amount of keys that need to be shifted will be the amount of keys that each node contains times the amount of duplicates that exist for it on the ring. So in this case, A has n by k into m keys. So you'll have to shift them to the adjacent nodes if A goes down, and also shift it for its duplicacies over here. So on rebalance, the keys that have to be shifted is n by k into m times k, which is n over m. So you can see that you don't have to move all keys around if a node enters or leaves the picture. And we can also see that if m increases, the number of shards increases, which in a scalable, constantly growing system is very likely. Consistent hashing becomes pretty ideal and becomes growingly efficient. With this, we come to an end for partitioning. In the next section for this video, let's talk about implementing linearizable databases. We'll start off with a very brief revision on version vectors, and that will be a perfect segue to Lamport clocks, logical timestamps. So this is going to be pretty quick. Version vectors, as we've seen, help protect causal dependencies, and we can resolve conflicts during replication. So let's say you have P1 and P2. This is P1 state and this is P2 state. And clearly P1 is outdated compared to P2, and P1's data will be replaced by whatever data is there in P2. So P1 will update itself with P2's data. In the case of concurrent writes, over here you have non-overlapping entries. So one vector does not completely dominate the other vector. So in this case, P1 and P2 will have to resolve this between themselves, either using manual intervention. You can store the sibling values, or you can use CRDTs. Let's look at this particular flow over here. You have write 1 taking place on node A. So you'll have 1, 0, 0. You'll have write 2 taking place on node B, 0, 1, 0. And then A and B will replicate between themselves. So in this case, you see that there is a concurrent write between them. There's a conflicting write. So they'll resolve this, let's say using CRDTs. And the final state at the end of this is 1, 1, 0 for both A and B. So the inference is that W1 is conflicting with W2. They are concurrent events. After this, you have W3, write 3 that goes on node B. So after being in the 1, 1, 0 state, you have a write 3 that comes on node B. So it'll be 1, 2, 0. And then you have a write 4 on node C, which is 0, 0, 1. So node C is completely oblivious to all the drama that took place between A and B. So the inference that you can see from here is that W1 is obviously concurrent to W2, and that this W4 is concurrent to every single thing that happened before it. So W1, W2, W3 are concurrent to W4. So you can see that W1 will determine W3. So W1 over here is dwarfed by W3. So W1 determines W3. We also know that W2 will also determine W3. And we know that W1 is concurrent to W2. And W4 is totally oblivious to everything. So W1, W2, W3 are totally concurrent to W4 that happen independently. Now, if I were to generate a ordering for these events, I know that I could place W1 first, then I could place W3 over here. But where could I place W2? I can't place W2 above W1. They are concurrent transactions. Nor can I place W2 below W1 because W1 didn't necessarily happen before W2. They're concurrent transactions. So I can't maintain a definitive sorted order of these writes, of these events. What I can do is maintain a partial ordering of them. So in partial ordering, only some writes can be definitively sorted relative to each other. Concurrent writes will obviously remain unordered. There's no guaranteed ordering between them. So version vectors will provide partial ordering. So again, based on the example we've seen, one partial ordering can be W1 comes before W3. Another partial ordering is W2 comes before W3. But we can't maintain an ordering, or we can't write an ordering between W1 and W2. They are concurrent transactions. Nor can we talk about W4 over here, because W4 is a concurrent transaction that is oblivious to all these events. But we can say that this is for certain, W1 came before W3 and W2 came before W3. This is for certain. So you can maintain a partial ordering of these events only. You can't maintain a partial ordering of all pairs of events. If it was possible to maintain a partial ordering of all pairs of events, let's say it was W1 here and then W2 here, then W3 here and W4, this would be called a total ordering. But as we've seen, version vectors don't provide total ordering, they provide only a partial ordering. A total ordering, in contrast, would force every pair of events to have a definitive sorted order, even if they were concurrent. And the way that we could have implemented total ordering over here is, let's say, along with the events, let's also append the timestamp. So let's say W1 and W2 were concurrent events, but let's say W1 happened at 10 p.m. and W2 happened at 11 p.m. Then in that case, W1 will be before W2. So in order to implement total ordering, what you can do is, along with the event that happened, you can plug in some artificial tie-breaking scheme, which in this case could either be the node name. So let's say node A will be always before node B, or it could also be the timestamp of it, 10 p.m., 11 p.m. So if you have E and A, and then you have, this is E1A and you have E2B, and you've decided the artificial tie-breaking scheme will be on the basis of the node name, where B comes before A, and let's say these are concurrent events, then the final sorted order will be E2 comma B and then E1 comma A. So we can use either global physical timestamps, but as we've seen in the previous videos, it is not a good idea to rely on physical timestamps in a distributed setup, because your timestamps are generated with the help of the quartz crystal oscillator, and this is an electromechanical device, and through time, over time, you can have clock skews. The frequency can alter. You'll have the clocks drifting. A better approach to ordering events is using logical timestamps. So this concept was introduced by Leslie Lamport in the late 1970s in his research paper. It was initially a very novel idea to order events on the basis of counters, logical counters, rather than on the basis of time. And we'll go into Lamport's logical clock or logical timestamps in more detail in a short while. So what is the main idea of all this exercise? We are mainly focused on having total ordering of all our events in our system. So let's say this is a database node 1, database node 2, database node 3, and they each get events. Let's say this gets event E1, this gets some write event E2, E3, so on and so forth. After that, the main goal of having a linearizable database is I should be able to maintain a sorted order of the events that have taken place across my system. So this is a total order or a total sorted order of all the events in my system, and all the nodes should be in agreement of this particular order. So there are two things over here. I want to implement a linearizable system. Linearizable means every single write that happens in the system across these different nodes, I should be able to create a total ordering of all these writes, of all these events, E1, E2, E3. And number two, all the nodes should be in agreement of what the sort order is, of what the total ordering of these events is. Why do we need this? Why do we even want to implement linearizability? Why do we even care about total ordering? As we'll see in the later sections, there are quite a few practical applications for it, practical use cases for it. Let's first understand logical timestamps in a bit more detail, the math behind it, the principle behind it, and then let's take a look at some applications where we care about total ordering, where we care about linearizability, where we care about these different nodes being in sync, being in agreement with what the total ordered state is. So while a version vector requires linear space, if you have n nodes, the version vector will have n slots. Lamport clocks require just constant space. They just have two things. One is the node ID, and the second one is the logical timestamp, the event counter. So both are used for different purposes. Version vectors are used to track causal dependencies. They're used in replication to check for concurrent updates. And if there is, we need to have a conflict resolution between them. Lamport clocks are not used for that. Lamport clocks or logical clocks are used for ordering events. We have two totally separate use cases. So Lamport clocks, just like version vectors, will also provide partial ordering right out of the box. So you need to provide some artificial tie-breaking scheme to have total sorted order. So in this case, we make use of the logical timestamp along with the node ID. So the artificial tie-breaking scheme in this case will be the node ID. So in this case, let's say we have that A has a higher priority than B, and we have the events A1 and A2, and we also have B1 and B2, then the sort order will be this over here. So we break the ties with node IDs. In total ordering, every pair of events will have a definitive happened before relationship. All events can be arranged in one straight line. So they require artificial tie-breaking rules or a central coordinator over here. So a quick summary of the things that we've covered so far. We care about total ordering of events in our system in order to maintain or implement linearizability. This is helpful for certain applications, which we'll see in a short while. We've also seen version vectors and Lamport clocks. They both are different data structures. Version vectors is linear space. Lamport clocks is just two things over here, constant space. And they both serve distinct purposes, different purposes. Version vectors are for replication. They help track causal dependencies. You can quickly determine if a particular node is lagging behind in terms of updates, or if two nodes have received divergent updates. And in that case, you can quickly detect if they are conflicting, if they are concurrent writes. And in that case, you'll have to resolve them. Version vectors, I mean Lamport clocks, on the other hand, the logical timestamps, they serve a totally different purpose. Their main goal is to just provide simple ordering of the events that happen in our system. They're not related to replication. We just care about linearizability. We just care about ordering. So we make use of logical timestamps. So let's see how to order writes with the help of logical timestamps, with the help of Lamport clocks. So one is, what if we have a single leader replication setup? So you just have one node along with its followers. So in this case, events, writes are inherently ordered. You have event E1 coming in, then event E2, and then event E3. And this is just on one node. And this node can just directly ship the replication log, and all the nodes will be in agreement that, okay, these are the events that have happened, E1, E2, E3. We don't have to care about sorting events across nodes, because one node over here is the sole leader, and it is the only node that is getting these events. So it's inherently ordered. Just ship the replication log as is. Things become a little bit more complicated when we deal with a multi-leader or leaderless setup. So you have these different leader nodes making independent decisions, having independent events that come in. So E1, E2, E3 over here. And there's no definitive sort order to guarantee saying that E1 happened before E2 or E3 happened before E4. We know that within a particular node, we can say that, okay, E1 happened before E3, and within a particular node, E2 happened before E4. But how do you sort events that happened across partitions? So in this case, you make use of the Lamport timestamps, of the logical timestamps. So let's see the working theory of Lamport clocks and what was proposed in his research paper. So let's say you have a client over here, U1, user 1, you have user 2 over here, and you have database nodes A and B. The initial timestamps that are configured on all these nodes and all these users will be 0. Now, when user 1 wants to write some event on A, it sees what is its local timestamp, it's 0. And it sees what is A's local timestamp, it is 0. So when U1 writes something to A, it will make that write, let's say X, along with 1. So U1's timestamp will change to 1, and even A's timestamp will now get promoted to 1. Now, let's say U2 also wants to write something to A. So in that case, U2 will see that, okay, my value is 0, but A's value is 1. So when U2 wants to write, let's say Y, it will not write 0, it won't write 1, it'll write 2. So the new write value will actually be 1 plus the max of my value comma, the node that I'm trying to write to. Now, based on this example over here, U1 made two writes to A initially. It made the first write, its value became 1, A became 1. It made another write, so its value is 2, even A's value is 2. Now, when U2 tries to make a new write to A, A's value will get promoted to 3 and even U2's value will be 3. Now, let's say A sends something to B. Now, in this case, when A sends something to B, B will get promoted to 4 and not 1, because A, when it sends that message, let's say Z, it will send Z, comma, the max of 1 plus my value, which is 3, comma, the one that I'm trying to write to. So it'll be 4. So in this way, in this setup, you can easily create an ordering of the events that have happened. So you know that 1 happened first, 2 happened second, third happened third on A, and fourth happened on B. So you have A1, A2, A3, and B4 over here. So you can easily maintain an ordering over here, right? A total ordering. So what are the mathematical properties behind this? If A precedes B, if A causally determines B, then for a fact, the Lamport timestamp of A will be less than the Lamport timestamp of B. However, if Lamport timestamp of A is less than Lamport timestamp of B, it does not imply that A causally determines B. It could be that A and B are concurrent writes, concurrent events. What does all this mean? Let's break it down. So let's understand the first property, that is, if A causally determines B, then for a fact, the Lamport timestamp of A will be less than the Lamport timestamp of B. So over here, initially, U1 made two writes to A, so it got promoted from 0 to 1, 1 to 2, and then U2 made another write to A, so it got promoted from 2 to 3. Now, A is trying to write something to B. Let's say it's a distributed transaction, something happened over here. So A is trying to write something to B. Now, when it tries to write to B, B's value will get promoted from 0 to 4, right? So in this case, it's obvious that, well, 3 is less than 4. So this property holds true. The Lamport timestamp of A is less than L of B. But let's say B had some other writes that took place before all this happened. Let's say you had a user U3 that wrote 0, that wrote 1, that wrote 2, that wrote 3, that wrote 4, and that also wrote 5 to B. Now when A tries to write something to B, what will it write? It'll write Z, comma 6, which is the max of A's value, comma B's value plus 1. So it's going to be max of 3, comma 5 plus 1. So again, in this case, the Lamport timestamp of A, which is 3, is less than 5. So we can state definitively that if A causally determines B, if A is trying to write something to B, the end outcome is that B's timestamp is going to be greater than A's timestamp. So the L of A is going to be less than the L of B. But we can't say the inverse will always be true, that if the L of A is less than the L of B, we can't necessarily state that A causally determines B. Why is that? Let's take the simple example. You have these two nodes, which is node A and node B. Let's say node A gets two writes, 1 and 2 from some user, and node B will also get, let's say, a few writes from some other user. So it'll be promoted from 0 to 1, 1 to 2, 2 to 3. Now the L of A is 2 and the L of B is 3. 2 is less than 3, but can you necessarily say that A causally determined anything in B? No, that's not true. These were independent writes that took place. Your Lamport timestamps, when you put it this way, means nothing. 2 less than 3 means nothing. It could either be that A causally determined B, or it could also be that the events in A and B were concurrent events. So you can't necessarily state that if L of A is less than L of B, you can't necessarily state that one event causally precedes the other. By the way, over here you have A having events 1, 2. Even B over here has events 1, 2. So how do you perform a total ordering in this case? So we need to rely on some artificial tie-breaking scheme. Let's say that A is having a higher priority than B. Then in this case, A, 1, B, 1, A, 2, B, 2, and B, 3. That will be the total ordering for the system. So going back over here, Lamport timestamps don't help us in causal dependency detection. Then what does help determine causal dependency detection. Version vectors will help us in causal dependency detection. And this is very useful when you talk about replication. So Lamport timestamps don't help us in replication, they just help us in simple event ordering. So this is another example to drive home the point. You have these three different processes, these three different nodes, and A initially gets this right from some user, 1A, even C gets this right, 1C. So you can see that 1A and 1C are concurrent events. Then after 1A, it gets another write from the user, 2A. And after this, A tries to write something to B. So the value over here will be 3 comma B. So you can see that 2 comma A will causally determine 3 comma B. And the Lamport timestamp of A is also less than the Lamport timestamp of B. 3B will then have another event. Node B will have another event, 4B. And after this event, node B will try to write something to C, and it'll be 5C. So you can see that 4B will also causally determine 5C over here. But you can see 3A and 5C are totally independent. So even though the Lamport timestamp of A is 3, which is less than the Lamport timestamp of C, which is 5, you can't say that 3 comma A determined 5 comma C. There's no line that goes from here to here to here. So it just is a physical insignificance that the Lamport timestamps are less. It has no practical value. You can't definitively say that A determined C, or you can't definitively say that 3 comma A determined 5 comma C. But if you see a direct line over here, so there is a line from 2A to 3B, and then 3B to 4B, and then 4B to 5C. So indirectly, 2A has determined 5C. So in this case, the Lamport timestamp is less in A compared to C. By the way, these events need not necessarily be write events. They could also be read events. They could also be processing events. Basically, whatever ordering that your system needs to do, it can be done basis on that. So if you just want to order write events, you can just keep track of that. So let's understand what exactly does 2A talking to 3B mean, 4B talking to 5C mean, and all these lines. Let's understand with the help of this example. So let's say you have a booking system and A gets this request, a login request from some user, and then A will talk to node B and send in the parameters that it received from the user, the username and the password. So that could be one event where it's sending something to B. 3B to 4B could be some processing event that happened. 4B to 5C could be node B validating the user and then sending a log entry write message to C. So basically telling C, make this log entry that this particular user has logged into the system at this particular timestamp. So this could be one practical use case where you have these different nodes, these different processes talking to each other, and where you can basically visualize how one event indirectly determined this event. So 2A was the, let's say, initial login request, and 5C was the final log entry output. So 2A in a way determined 5C. So in conclusion, Lamport clocks or Lamport logical timestamps help in total ordering of events in our system. If event A causally precedes event B, then for a fact, the L of A will be less than L of B. But you can't say the inverse will always hold true. If L of A is less than L of B, you can't necessarily state that A causally determines B. It could be that A and B are concurrent events. So we've seen that Lamport's clocks or logical timestamps help in providing a total ordering for all the events. Now let's see, why do we even care about having total ordering of events in a distributed setup? There are certain applications, certain use cases where it is crucial for us to have a consistent sorted order of all the events. Let's take a look at some of these examples. The first one is to implement distributed mutual exclusion or distributed locks. So you have these multiple nodes and they work on some shared piece of data and they need exclusive access to it. And let's say we don't have any central coordinator over here that keeps track of what resources being owned by which node, or it keeps track of the status of the locks. You don't have a central coordinator over here. So you need to come up with a distributed solution. And the key point over here is you should ensure that only one process enters the critical section at a time. So how do you use logical timestamps over here? How do Lamport clocks help? First, each process or each node will maintain its own Lamport clock. That is obvious. When a process wants to enter a resource, it sends its timestamped request to all the other processes. Point 3. All processes are in agreement with the processing order of requests, and the process who wants to enter the critical section should receive approvals from all the other nodes. Only then can it access the critical section. So let's say you have this node P1, it wants to access R. So it will send this event to all the other nodes that are there, P2, P3. Let's say we just have P2 now. So it sends 1, P1. Even P2 wants to access the critical section. So it will also send 1, P2. Now in P1's queue, you have its own request 1, P1, and you also have the request coming in from P2. Similarly, in P2's queue, you have the request coming in from P1 and you have the request coming in from P2. Now these events are obviously concurrent events. They are not related to each other. They're not causally dependent on each other. So if you want to have a total order of these events, let us make use of this artificial tie-breaking scheme, and let's say that P1 will have a higher priority than P2. Now all the nodes, when they receive these events, they'll arrange it in this particular sorted order, 1, P1 and then 1, P2. So P2 will see that, okay, P1 wants to get the lock and P1 has a higher priority. It's in the front of the queue. So P2 will send a accept message to P1. So once P1 gets approvals from all the other nodes, P1 sees that it is also at the front of the node and it will access the critical section. Once it is done, it will obviously remove itself from the queue and send the same message to all the other nodes. So even P2 will remove P1 from the queue. Then P2 will process the next node, which is at the front of the queue, which in this case is itself. So in both P1 and P2's queue, the request will be sorted in the same order. And how are we able to sort this in the same consistent order? With the help of logical timestamps, with the help of this one. The second use case is for consistent event logging. So you have these different nodes in your system. They each do different tasks. Let's say this is the user login. You have one event over here. After login comes authentication of those login credentials. So you send that event to this particular node. This particular node will process those credentials, the username, password, send some event back to this. This node might then send some other message to a third node, so on and so forth. So these events over here could be tied up together, and they each will, let's say they each will maintain some log entry once they process that event. So when all is said and done, what you expect is to have one common log file, and this log file will have event E1, event E2, event E3, the logs for them. So you want to have one common global log that will help you in debugging the system. So let's say you have a web server, which is process P1, it gets LC1 login request, and in the next event, it sends some query to the other node, and in the third event, the login is approved. That DB2 will receive this particular query, it'll process that and send the result back over here. So you can see LC1 here, LC2 here, LC3, LC4, LC5. So they are all causally dependent events in this case. Similarly, you have an authentication service over here, and let's say you have some other services P4, P5, which have independent concurrent events going on. You expect to have a unified collated log from all these nodes. So we can have an artificial tie-breaking scheme where P1 comes at the forefront and then P2 and P3, and you can arrange the events in this order: LC1, P1, LC1, P3, 2P1, 2P3, so on and so forth. So when multiple servers or processes are generating events and you need to create a unified picture that shows events in a causally consistent order, you can make use of logical timestamps. So this is the second use case for it, to create a unified log in a distributed setup, consistent event logging. I'm going to go back to the first example where we talked about distributed mutual exclusion. One assumption that we made over here was that all the other nodes P2, P3 will get the events in the same order at the same time. So over here, when P1 broadcasts 1, P1, and when P2 broadcasts 1, P2, We are assuming that P3 will receive those messages at the same time, and only then will sort. So over here it will come 1 comma P1, and over here it will be 1 comma P2. But again, we're dealing with a distributed setup. What if we have a node P4 and P4 gets 1 comma P2 first, and it doesn't receive 1 comma P1? Maybe the message is lost, or the message will take quite some time to reach P4. Then in this case, P4 will just proceed with executing this event 1 comma P2, which is wrong. So if we had 1 comma P1 existing in the queue, then okay, P4 could have known that 1 comma P1 should come before. It knows the sort order. It knows that if 1 comma 1 and 1 match, P1 should have a higher priority than P2. But there's no P1 over here. Only P2 reached over here quickly. So this is a major limitation with the approach that we're going with so far. While, yeah, we do have a mechanism to implement total ordering for all our events in our distributed setup, but what is the point of having the total ordering when those nodes themselves, each individual node in our distributed system, might not honor that the processing of those events in that same sorted order? We require all the nodes over here to have the same consistent view of what the total order is. P4 thinks the current total ordering is just 1 comma P2, while P3 thinks the current total ordering is 1 P1 and then 1 P2. This is wrong. So while Lamport timestamps help us to provide a total ordering for the events, but just doing that is not enough. What we also need to guarantee is that all the nodes are in sync, are in agreement with what the total order is. So what are some common flaws when we deal with just Lamport timestamps in a distributed setup? So one is you could have message loss. You could have network partitions when you transmit these events across the nodes. Logical clocks, Lamport clocks, will just give you a partial guarantee of linearizability. They tell you what the correct sort order should be if all the messages were delivered correctly. But we also need to guarantee that the messages are delivered reliably and correctly, that all the nodes receive the events and that they are in agreement with what the sort order is. So we need consensus, distributed consensus among the nodes regarding what the sort order should be to impose linearizability. So again, Lamport clocks will just tell you what the sort order should be. But just doing that is not enough. You also need the nodes to be in agreement that yes, this is the sort order. So the node should have a consistent picture of the total order state. Linearizability requires all operations to appear to execute in a global total order consistent with time. So Lamport clocks are just tools that help in the sort order. But to actually achieve linearizability, you need both Lamport clocks plus consensus among nodes about what the sort order is. It shouldn't be that one node has received event E1 and E2 and processes E1 first and then E2, and you have another node that just received E2, E1 got lost, and it proceeds to execute E2. This is wrong. You want all the nodes to be in sync about what the sort order, the total order of the events should be. So you want both these nodes to be in sync that the sort order should be E1 and E2. Let's take a look at another practical use case for logical timestamps. It is used to implement optimistic concurrency control in certain databases. So if you recall from the video on asset transactions, video 3, we went into detail on some dummy implementation for an OCC database. So in this case, you have a data item X, and every single new transaction that tinkers with X will have its own version. So transaction T1 will start off with version V1, and any new tinkering from transaction T1 for this data object X will create a new node with version 2. Similarly for transaction T2, it'll start from version 1, so on and so forth. So you're making use of the logical timestamp concept over here. Let's take a look at the last use case for the logical timestamps. So if you recall from the last video on replication, we talked about the monotonic read problem. So when you deal with a multi-database node setup and when you have eventual consistency, you can have your reads going back in time. That is a problem. So you want to implement monotonic reads. So if a client reads a version V5 at time ti, subsequent reads should be greater than or equal to version v5. So let's say this is your database node over here, and you have the version of X, and let's say it gets updated initially at v1, and then you have some v2, and then you have some v3. Let's say you have the followers of this particular node over here, and it gets replicated with X equals version v3, which is the current latest version. So if a client were to read the value of X, he'll get the version v3 at this point. But now let's say the leader gets a new update for X, and that'll be v4. So now if a client reads from X, reads X from the leader, it'll be v4. But let's say the next time the client does another read of X, and this time the read request gets directed to one of the follower nodes, and the follower nodes are not yet updated. So now the client, before it read v4, but now after getting directed to a follower, will read v3. So your reads are going back in time. So this is an issue. And how will Lamport clocks help? So when a client performs a read, it can record the highest Lamport timestamp it has seen. So when the client has read from this particular leader node, it can record that, okay, it's version v4 that it has read. So the next time the request goes to a follower node, the client will know that, okay, the follower node has returned a stale value, a stale version, so it can just safely discard it. And subsequent reads can just be directed to any node which has greater than or equal to v4. So when a client performs a read, it can record the highest Lamport timestamp it has seen. And for subsequent reads, the client can just request data only from those replicas that have at least that timestamp. So this is a real use case for Lamport timestamps. So to conclude with the concept of Lamport clocks or logical timestamps, it is for the most part just a theoretical concept. It's just in paper. In practice, we don't make use of plain logical timestamps as is. It has very few applications in real life, and we've tried to fit in 2 or 3 examples to demonstrate the idea using distributed logging or using distributed mutual exclusion and using the optimistic concurrency control examples. But in real life practical examples, just using plain logical timestamps has very little value. It is mostly useless. As we've seen earlier, in order to implement a linearizable system, you need both event ordering, plus also you need to have distributed consensus among the nodes. They should be in agreement with what the ordering of the events are. So just using plain timestamps, logical timestamps are useless. But when they were introduced in the late 1970s, in 1978 by Leslie Lamport in his research paper, it was a pretty novel, unthought of idea at that time to order events on the basis of logical timestamps rather than using physical timestamps. In fact, the concept of Lamport clocks gave rise to version vectors. And as we all know, version vectors are way more powerful than Lamport clocks. They track a lot more information than Lamport clocks. They can help track causal dependencies, and they can help track if certain events are concurrent or not. That is way more powerful, and that has way more applications in real life. One instance of it is in distributed databases where you have different leaders accepting different writes, and you want to track these writes. You want to make sure these writes are in sync when you're trying to replicate. You make use of version vectors in that case. So here's another use case for version vectors. It is used in distributed version control like Git. So this is the repository state. You're working on one repository on different branches. So developer 1 adds a feature in his branch. Let's say it's tracked by node 1. Developer 2, who is in some other country, will build on developer 1's work. So he sees the commit made by dev 1 or node 1. He fetches that into his local node and works on that. But developer 2 continues making independent changes on his branch. So it's 200 at this case. So his node is oblivious to whatever changes dev 2 is making. But then when it comes time to merge, let's say dev 2 wants to merge with whatever changes dev 1 has made, you will take dev 2's state, which is this, and dev 1's state, which is this, and you'll come up with a final version vector. So all this is possible with the help of version vectors, which help track causal dependencies. And what brought version vectors out into the world? It was the idea of Lamport clocks. Lamport clocks gave idea to the concept of version vectors, which is actually practically used. So in conclusion, Lamport clocks is for the most part a theoretical concept designed to implement event ordering that helps us construct a linearizable system. We've seen some few applications where we really care about having linearizable systems. Linearizable system is one in which the events globally can be ordered in a total ordered fashion. One is in the case of distributed mutual exclusion, and the second one is for distributed logging. While it still can be used practically in some isolated cases, but for the most part, it is a theoretical concept that paved way for version vectors and consensus algorithms. So consensus algorithms like Raft, Paxos is what we'll discuss in the next section, and they implicitly make use of the logical timestamp concept. So as we've seen earlier, just using Lamport clocks is useless. They just provide a total ordering. But in many cases, in fact, in most cases, if you care about linearizability, you also care about strong consistency. And you want all the nodes of the system to be in sync, in agreement with what the state is. So we care about consensus over here. So in the next section, we'll talk about one consensus algorithm called Raft. So for situations where multiple nodes need to agree on the order of events and process stuff in the same way, using simple logical timestamps won't help. We need distributed consensus. In comes Raft. So Raft is an algorithm that helps us achieve distributed consensus among the nodes. So let's say this is one node over here with some fallback or follower nodes in this case. What Raft guarantees is two things. Number one is all the events in our system will be linearizable. So if the leader gets event E1, event E2, event E3 in that order, then all the other nodes will also process those events in the same order. So Raft will guarantee linearizability. Point number one. Point number two, Raft will also help guarantee fault tolerance. So let's say the leader node over here gets event E4 now, and the leader node will then die. So what Raft guarantees is that the next leader that pops up from among these nodes, it is guaranteed to have event E4. So if the leader node gets event E4 and the leader node sends a commit success message to the user, and when the leader node dies, the next leader that's going to pop up is definitely going to have E4. So Raft guarantees linearizability and Raft guarantees fault tolerance. You will be using Raft in your application code where you really care about consistency, where you really care about consensus among the different nodes, where you really care about fault tolerance. So one example could be in the case of financial applications. So let's say you have a booking application, Book My Show, and a small module, a small service of that could be related to payments. So if a user does a certain payment, that's some event E1, you want to make sure that you have fault tolerance, that you replicate that particular event to all the follower nodes. So event E1 is replicated over here in a fault tolerant fashion and in a linearizable fashion. So after, let's say the user makes a payment in this case, and let's say the user then does a refund status that comes after E1, that's event E2. So you want to process these events in the same order. So in such cases, you make use of Raft. So Raft consists of two stages. One is the leader election stage, and the other one is the Raft write stage. So Raft calls for just having one leader over here because you're dealing with a very critical section of whatever service you're trying to implement. Let's just have one leader. So Raft is a single leader consensus protocol. If you need to have multiple leaders or nodes, you can make use of variants of Raft libraries, which is multi-Raft. So you can have one Raft group over here with one leader with its followers, and another Raft group over here with leader 2 with leader two's followers. And these two leaders can independently take in writes. They'll within the group, you'll have fault tolerance. So any write that is committed is guaranteed to be persisted among the followers. So if the leader goes down, the new leader will have that right. And periodically, you can also have replication between the two leaders. So you can make use of version vectors in this case. So any new write that the leader has, update the version vector, periodically update the different Raft groups. And if you find a collision in the version vectors, you have to resolve it either manually or using CRDTs. Though in practice, for the most part, you don't make use of multi-Raft, you'll make use of single Raft. So in practice, each Raft group ideally is a partition range and it's not a geographical replica. So the only case where you'll actually be using multiple graph groups is if each leader deals with a certain range of data with a certain partition. So let's talk about the first stage in Raft, which is choosing who the leader is. So the entire point of the exercise is to ultimately build a linearizable system where the majority of nodes are in consensus with what the current state is. And this helps ensure strong consistency. So we'll have just one single leader node accepting writes, and it asynchronously replicates it to its followers. And some followers can obviously lag. So the way that we are replicating it to the followers is by using the quorum consistency model. So if you recall from the earlier video, we talked about quorum consistency, which helps us achieve strong consistency. So what quorums calls for is when you have a new write it to a quorum nodes, which is a majority nodes. And when you read it from a majority nodes. That way you'll always read the latest version. So Raft algorithm makes use of this quorum concept. So when you have a leader over here and it gets a new write, let's say to write event E1, before sending the commit success message to the user, it'll first write it to a quorum nodes. It'll write it to all the nodes, and only once it gets the quorum approval, it'll send a commit success message to the user. This way we can guarantee fault tolerance. So now if the leader were to go down, we can guarantee that some node in the follower list will have that event E1 written to it. So in Raft, we constantly send heartbeats from the leader to the other followers. And if the leader is down, one of the followers will pick this up and will take the initiative to trigger the next leader election process. So let's take this scenario. You have the single leader over here, and it is the leader for term 5. And let's say you have 3 followers over here, and follower 1 and follower 2 are following this leader, who is the leader for term 5. Follower 3 over here is lagging behind. It's still in term 4. Let's say it was down for the longest time and it just recently came back up, and it was unaware that you had a new leader over here who was elected in term 5. So now if the term for the downed leader was term 5, the new candidate among the followers who is going to propose the next election will propose that election for term 6. So a quorum of nodes will then get the message, I am F2 who wants to be the leader for term 6. Do you want to follow me? And if it receives an approval from a quorum nodes, that node is then going to be the leader. So over here, let's say F2 starts the election process for term 6 and F2 reaches out to F3. And let's say F3 is a follower for term 3 or follower for term 4. So it's severely lagging behind. Now when F2 proposes that, hey, follow me for term 6, obviously F3 will readily accept because it knows that 3, 4 or 5, whatever term number it was following is severely lagging behind and follows F2 for, it supports F2 for term 6. Now what if you have F3 who is the leader for term 6? It could be that F3 has also started the leader election process in parallel to F2. Now when F2 is saying, hey, elect me for leader 6, F3 is going to say, no, I'm already the leader for term 6 and I already started the leader election process. So it sends a rejection. Now what if the node you're reaching out to also has the same term number from when you started? So you are F2, you are follower 5 and you want to be leader 6 and you're reaching out to F3 who is also follower 5. Will F3 accept or will F3 reject it? The solution is to compare their logs. The leader will be one who has the most up-to-date log entry. So you're making use of the concept of events or lamp or timestamps in this case. So let's say in F2's entry for term 5, it had the event E1 and event E2. But F3 for term 5 just had event E1. Then in this case, F2 will win. So F2 will get the support from F3. So only if the candidate receives a positive quorum vote, it becomes the new leader and it forms the new leader for a new term number. So why does this work? Why can you guarantee linearizability in this case? So number one, there's only one leader over here that's accepting rights, and you need to have votes from a quorum majority. So this is bound to give you just one leader, and it's very easy to achieve strong consistency as a result. Number two, all leaders that were down and now that have come up can't be the new leader. Why is that? Because of the concept of the epoch or term number. So you had F2, which was previously following F1, who was the leader for term 5. Now F2 is the leader for term 6. Now let's say F1 comes back up and it's trying to perform the leader election process, or it's trying to send rights to its followers in term 5. Now F2 is going to see this and say that, hey, F1, you were the leader in term 5, but I am the new leader, term 6. Or let's say F1 sends it to F3, who is the follower for term 6. It follows F2. So F3 is going to straight away reject the rights that are coming in from F1. F3 sees that it's a follower for term 6 and term 5, F1 is outdated. So all leaders can't come back up due to the epoch or term number. Number 3, leader is bound to have the up-to-date logs and it can backfill stale nodes. So what does this mean? So let's say F2 and F3 from the previous example, they were following term 5, and F2 just happened to have more log entries. Let's say those log entries, the messages dropped or are yet to be received on F3's end. So F3 just has one event from term 5. So now when F2 becomes the leader, F2 will backfill F3 with these two nodes. So F2 sees that F3 is lagging behind in terms of two events. So he'll just backfill it with event 2 and event 3. So backfilling of stale nodes becomes possible because the leader node is bound to have the latest and greatest state of the log. So the leader is bound to have the most up-to-date log over here. Let's take a look at this scenario. You have F1, F2, F3, F4, F5, and F1 triggers the new leader election process and it receives approval from F2, F3, F4. So you can see that 1, 2, 3 is its state and it readily receives approvals from F2, F3 and F4, the majority of nodes. And F1 then becomes the leader. But if you look over here, F5, let's say F5 is in some separate continent and it didn't yet receive the leader election process from F1. So it couldn't send a no. Even if F1 gets one proper no, it won't be the new leader. But F5 didn't get a chance to send a no. But we know that from here, F5 has 1, 2, 3, 4, 5, which is objectively the latest and greatest state. So what if F1 consults and gets approval from a quorum? F1 then becomes the new leader. And now a new leader is going to have stale entries. It's not going to have the latest and greatest log entry state. So how do you resolve this issue? The thing is, you don't have to resolve it because Raft will guarantee that the situation never will arise. Raft guarantees that any committed entry for a node will also reside on a quorum nodes. So if the leader dies before replicating to a quorum, this does not hold. Because if the leader dies before replicating to a quorum, you won't be sending the commit success message to the user to begin with. So let's say over here you had 1, 2, 3, 4, 5, which was the leader in the previous state, and it replicates it. When it replicates it, it should replicate it to a quorum number of nodes and only then send a commit success message to the user. So let's say it was unable to replicate it to this F1 over here and its state is still 1, 2, 3. And now let's say this leader node dies. So in the next leader election process, you are bound to have quorum number of nodes that have state 1, 2, 3, 4, 5. Because you wrote the latest state to a quorum number of nodes should also have that latest state. So it is impossible for F1 to get the leader approval from a quorum nodes in the next cycle. I hope this made sense. So for the example earlier, if a node has 1, 2, 3, 4, 5, and it is the latest and greatest state, then for a fact, this state should exist in a quorum number of nodes, and only that leader which has this state will be that node which has the state will be the new leader. So that was it for the first stage of the Raft algorithm, which is choosing the leader. The leader should have the latest and greatest state in a linearizable fashion. The next is Raft reads. So the out-of-the-box implementation to read from a Raft cluster is to just read from the leader node. And you also have these follower nodes, but you generally won't be reading from the follower nodes. These are just as a fallback for fault tolerance. But let's say you don't care about strongly consistent reads. You just care about the leader having the latest and greatest state, and all writes should just go to this leader. Then in that case, you can just read from any of these follower nodes. And there could be a possibility that you read a stale entry But if your application does not care about strongly consistent reads, this should be fine. Let's now talk about the second and most important stage of Raft, which is Raft writes. So Raft writes is very simple. It's just a quorum write. The leader will receive a write from the client, append that entry for that timestamp to its log, and the leader will then broadcast the entry to all the followers, and only when it receives a quorum acknowledgement, it commits that entry. So from the previous video, we started off with quorum consistency. So if you have these multiple leader nodes that are capable of taking independent reads writes, and you want to perform a quorum read, you'll read from a quorum majority nodes, and you're bound to get the latest version. Similarly, when you write, you won't just write it to one leader node, you'll write it to a quorum nodes. That way you can ensure that whatever write you're doing is persisted in the system, and whatever subsequent reads you do, you will be getting the latest write. So we started off with that quorum concept. In this video, we introduced the concept of logical timestamps or Lamport clocks. We've seen what Lamport clocks are, we've seen the math behind it, and we also saw a limitation of Lamport timestamps, which is that it does not help us definitively guarantee if a certain event causally determines some other event. Those events could also be concurrent events. Lamport timestamps was a pretty novel theory when it was first introduced in the late 1970s, and it paved way to version vectors. Version vectors are what is practically used in modern day distributed systems. It helps us determine causal dependencies and will also help us resolve conflicts between different nodes when you're trying to replicate. Lamport timestamps as a concept also helps us in a few distributed use cases. We've seen a couple of them. One is for optimistic concurrency control. The other one is for monotonic reads, for distributed logging, for distributed transaction ordering, for distributed mutual exclusion. Lamport timestamps also is inherently used in the Raft algorithm. The Raft algorithm, we maintain event ordering, those concepts of events. Those are all Lamport timestamp concepts. The concept of having new term numbers, those are again Lamport timestamp concepts. So Raft not just makes use of logical timestamps in a way, it also makes use of quorum for quorum writes. So they are all really tied together. So if you have some subsection of your application, let's say the payment section, that absolutely needs strong consistency, you could either have these multiple leader nodes that can take in these different writes, these different events, and they'll do quorum reads, quorum writes among themselves. You'll have to implement that logic by yourself. Or let's say you don't get a lot of writes, the writes can just be directed to one node. Then in this case, you can just make use of the Raft library. The Raft library is meant to be used with just one leader node. So again, the benefits of using Raft for your subsystem is it provides linearizability in terms of the events. All the nodes will process those events in the same fashion and guarantee fault tolerance. If the leader were to go down, the new leader that comes back up will pick off from the same state that the previous leader left off with. Raft leaders, the major drawback is Raft reads or Raft writes, they are slow. Raft writes, when you write, you won't be just writing to one node. That node has to ensure that it writes it to a quorum majority nodes as well. And only then it sends a commit success message. So Raft writes are pretty expensive, and you'll use it sparingly in your application and only in certain sections of your application where strong consistency, where fault tolerance, where linearizability is very important. Let's end this video with a short segment on Zookeeper. So Zookeeper is a coordination service. A direct competitor to Zookeeper is etcd. So Zookeeper runs on an algorithm called ZAB, Zookeeper Atomic Broadcast, while etcd runs on the Raft algorithm. Now, when I say coordination service, I mean the exact same thing as a Raft cluster. So in a coordination service, all the nodes should be in sync of what the current state is. So when I talk about Zookeeper, I want to have the same mental model as a Raft cluster. So in a Raft cluster, you have one leader node, and on any new Raft write, it replicates it to the followers, and the followers are in sync with what the current state is, and they process those events in the same order. Zookeeper 2 does the exact same thing. So you have a Zookeeper cluster where you have the primary node over here and you have backup nodes in this case. So Zookeeper is exactly the same. Whatever you can do with Zookeeper, you can do it with a Raft cluster and vice versa, but they do have their differences. When you talk of implementing strong consistency, linearizability in your application code itself, for example, in your payments service, you want the payments to be linearizable. You'll be making use of Raft cluster. You will be making use of the Raft library in your Java application code. But when you deal with configuration related data, stuff that is not central to your core business logic, you'll be making use of a dedicated Zookeeper cluster. So Zookeeper, with the help of Zookeeper, you can solve the following configuration related use cases, like who is the current leader node, who currently owns the lock to some resource, who are all the members belonging to a Kafka cluster, how many nodes are dead or alive, what are the IP addresses of a particular node, what are the DNS resolutions for certain nodes, which shard contains what ranges of data, what nodes provide this service endpoint, what should the configuration setup or profile options be for a client coming from region X. So all this configuration related data will be directed to a Zookeeper cluster. So Zookeeper cluster will be some nodes, some computers where you will install Zookeeper, and just that, it'll just run Zookeeper nodes and it'll just maintain configuration related data. It won't maintain your application code. So configuration related use cases that are not actually part of your application code, you'll be putting them in a dedicated Zookeeper cluster. So the picture is exactly same as Raft. You'll have a leader, you'll have followers. So how does it differ from Raft? We'll see it in a short while. So you over here, you have your application code. Let's say this is server 1 running the payment service. This is server 2 running the booking service. And you want to get the primary DB, the leader node. So you will fetch that from the Zookeeper cluster and you will read it from the leader or one of the followers. So Zookeeper, the way it is different from Raft is it provides a hierarchical structure of Z nodes, or rather it just provides a file system. So if this is your Zookeeper node, the memory structure looks like this. So you'll have some root Z node, some root node, some root directory, let's call it config. And if you have some databases over here, some database related information that you want to store, you will store it in this particular Z node. Database usages with some data, who is the leader node with some data, some config related information for region A, you will store it over here. If you want to keep track of locks, what lock is owned by what node, you will keep that in this particular Z node, locks, resource A, the details of the node, of the client node holding that lock, so on and so forth. So all this information, this file system, this hierarchy is replicated to the other follower nodes in the Zookeeper cluster. So the Zookeeper nodes will themselves take care of replication, ensuring consistency among themselves. And we can separate out the Zookeeper cluster from our normal application code nodes. And our application nodes will only query the Zookeeper cluster for configuration related data. So there are some cases where some parts of our application code do need strong consistency, do need linearizability. So in that case, let's say the payment module of our application code, we can import the Raft library and use that in our application nodes over here. So in those cases where some parts of our application code need to have linearizability, in that case, we make use of a Raft library in our application code. So over here you have your application cluster and it can independently query the Zookeeper cluster, maybe to get the Kafka details or the primary database node details. So if this is your application code payments processor, it will check the balance and it wants to deduct the amount. So you will not just deduct amount from one node, you want to persist that information, you want to do a quorum write on it. So I'll be making use of the Raft library and deduct the amount. So it does not make sense to store application data in Zookeeper's file structure storage. Zookeeper is meant for configuration data, low volume of data storage. So it does not make sense to store client data, which could be pretty large, in Zookeeper nodes. So application data belongs to application databases, and depending on your application's use cases, if some certain modules of your service require linearizability, you will be making use of Raft and interact with your application database to store application related data. But if you want to deal with configuration related data, lock time, uh, logging parameters, configuration related parameters, primary node details, nodes that are currently active, you'll be making use of the Zookeeper cluster. Now, again, you can create your own sort of configuration related cluster, your own mini Zookeeper cluster using Raft or using manual quorum reads and writes, but it is pointless and it is overkill. So you could write your own cluster using the Raft library to set or get the primary DB name, the nodes in a Kafka broker, the list of alive nodes. But this simple setting or getting can be done very easily, and it's managed for you in Zookeeper. All you have to do is to just create a Z node, create a directory, and plug or read it from there. So the overhead involved is very minimal. And in addition to that, Zookeeper will take care of ensuring linearizability and fault tolerance, just like Raft library. So in short, if certain modules of your business code require strong consistency, you're going to make use of the Raft library in your application code. But if your service requires the use of some utility configuration that is not critical to your business logic, you'll be making use of a dedicated Zookeeper cluster. So some concluding remarks: coordination services are built on top of distributed consensus algorithms. They're designed to manage low volume critical configuration data for distributed systems. And they ensure consistency in environments where multiple nodes need to agree on a shared common state. Some of those agreements could be on who is the lock owner for a resource, what are the server IP addresses, or what are the nodes containing the partition ranges. So as mentioned earlier, you have etcd, which is a direct competitor to Zookeeper. It makes use of the Raft algorithm internally, or you could also have the Zookeeper coordination service itself, which makes use of a custom consensus algorithm called ZAB, Zookeeper Atomic Broadcast. It is for the most part very similar to Raft algorithm. You do make use of quorums over here as well, but they have just very minor differences between them. Let's take a look at this scenario. Node A is the main service provider for operation XYZ, and node B is the backup for XYZ. And now the client discovers the service location using Zookeeper. Let's see how's that done. So when node A starts, it creates an ephemeral Z node or a temporary directory in Zookeeper under this particular location, on the services XYZ instance A. Same for node B. So this is the service registry that is done using Zookeeper. Now, if some client wants to access this particular service XYZ, it will query Zookeeper at that particular Z node. So it'll go to that file structure, it'll query that particular directory, that particular Z node XYZ, and see who is at the forefront of the list, and it'll see instance A is there. So they get a list and they choose the first one, say it's arranged on the basis of priority. Now let's say node A goes down. So if node A goes down, so this is the Zookeeper cluster over here, and this is the node providing service. Let's say this is node A who is providing service XYZ. So it is maintaining a constant connection to this Zookeeper node, a TCP connection. Now when node A goes down, the Zookeeper leader node will come to know that, okay, it's not receiving any heartbeats on this TCP connection. So it assumes that node A has gone down. So what it does is it deletes this particular node. It deletes the directory, which is instance A. So the client, other clients which rely on this particular service and they're subscribed to that particular Zookeeper Z node, they'll get notified that, hey, this node has been deleted, update yourself. So the clients watching subscribe do that. So if the node A crashes or disconnects, Zookeeper will delete it, and clients watching or subscribing to that get notified of it, and they'll update the node to subscribe to. So they'll update themselves to instance B. We'll talk about Zookeeper in a bit more detail when we deal with Kafkas in the stream processing video. Zookeeper as a coordination service is most commonly used in tandem with Kafka clusters. In the next video, we'll talk about batch processing. We'll discuss Hadoop distributed file systems. We'll talk about MapReduce and Apache Spark.